we are talking about how we use this navigation map. We start from the displacement field, definition of displacement field, and then we calculate the corresponding strain. And then next step, we calculate the stress, and then we check the force equilibrium. That is the procedure of analysis for any kinds of structural or solid mechanics system. Or instead of starting from your analysis from the displacement, you can start from the force equilibrium instead. And then finally, we finish our analysis by checking the compatibility condition. Okay, the last time that we considered this example, but there was some questions about the sign convention of internal forces. That's why I record today's video to explain the sign convention of internal force. Okay, let's look at the stress. So I already explained you the concept of the stress. Okay, say for example, let's imagine a part of a solid here, and then we have a material point. Let's say overall it is subject to tension. Then we can consider an imaginary cross section here. If you look at this cross section from the left hand side, then what happens is, okay, let's copy it. Actually, we can look at the same situation from both sides, from left hand side and also from the right hand side, for example. Okay, here we'd like to look at the same stress point from left hand side and from right hand side, and then we'd like to look at the same material point from the left hand side. And how do we define the direction of observation? The direction of observation can be defined by means of a unit normal like this. This is the right hand side. And then this surface or this plane can be quantified or characterized by this normal. Let's say because we are talking about overall intention, then there exists a traction here. So if you look at here, I must have this traction. This is traction. This direction of traction is heading to the right hand side, and then in this situation the direction of traction is opposite. This is very natural because of Newton's third law, action and reaction. Let's imagine that its magnitude is equal to sigma. So make sure that traction itself is a vector. Okay, so it is equal to defined as sigma, the magnitude sigma, and then its direction ex. Okay, let's imagine that this is our coordinate system x. Okay, and then here look at the second case. If you look at the second case, then situation is a little bit different. The magnitude is exactly same, but you know the direction is opposite. Magnitude is exactly same, but direction is opposite, isn't it right? Okay, look at this. The key concept is, so we are talking about same stress state, but depending on the observation direction, we have opposite direction of traction. Okay, the same stress state, but depending on the observation direction, we have different traction. This is the key concept you have to understand. That's why to represent this stress state, what we do is we have to use two different base vectors. The stress state can be written by, you know, its magnitude, and then direction of traction, and then the observation direction. So we need two normals. That's why if you consider, for example, in the first example, if you consider dot product Ex, then you're gonna have a positive sigma Ex. In the example in the right hand side, instead of just Ex, we have to consider minus of Ex. As a consequence, we have minus sigma Ex. Okay, we have opposite traction. Okay, this is what happened. Okay, let's consider, instead of dealing with traction, let's try to integrate. If you integrate this stress over the cross section, if you integrate the stress over the cross section, okay, over the cross section, then it becomes axial force. This is the vector. This is internal force. Okay, so conclusion is the internal force is integration of traction caused by the stress state, what I mean developed because of the stress state over the cross section. That's the meaning of internal force. Okay, so the sign convention of internal force should follow for the sign convention of stress because of this condition. Okay, so this is, instead of traction we consider stress tensor and the normal here. That's why we have to follow the same sign convention for the stress. If the member is stretched, then this actual force is positive as a default. And then this is, we consider the negative internal force. Okay, this is a brief summary regarding the sign convention of the internal force. Okay, I hope it will be very helpful.